Okay, I'm going to talk about discrete dynamic games. Let me get this resized properly. I'm getting better at being prepared. These slides were all opened up last night before I went to bed, and here they are. So, okay, discrete state dynamic games. Now, by the way, I'm only going to be talking about Markov perfect equilibria. Nothing today about super games. So these are going to be called stochastic games. We're going to be in discrete time and discrete state. And so it's the term stochastic game goes back. Oh, I should put the citation in there. It goes back to long ways. But then in economics, in empirical I/O, they became very popular after the Pacus-McGuire paper on how to compute the equilibria, Markov perfect equilibria of such games. And so that's what I'm going to describe today, as well as then the continuous time discrete state version of this. Now, so this is at first going to look like a lot like discrete state dynamic programming. And that's because it is a lot like discrete state dynamic programming. So the notation is very much like what you see in dynamic programming. The state of the game at time t is some omega of t. Now that state in the game could include many features of it, the nature of the level of demand, or cost function or whatever. But it also includes the states. There's a finite number of states for each possible player. And that's also in the list of omega here. And now player's action at time t is some element. This is a feasible set of actions when the current state is omega t, and that current state includes where what state a firm player is in. And then there's some actions that are available to the player. And then the player's actions at time t is just a list of the xt's. Now, the x superscript minus I notation is standard in game theory because it represents the vector of the x vector, but without the ith component listed. So it basically just is a vector of other people. So x here actions and omega denotes the states. Now, the state of the game. Now, for specificity, one could think of the state as being how many machines you have in your factory. And so there's some firms, and each firm has maybe, or how many factories, let's say, like Chrysler has many car factories, General Motors has many car factories. So basically how many factories you have. And so there's a, oh boy, okay. Sorry, there's so let me get this off the hook. So there's a transition probability process. So given whatever your state is today, given the state, maybe General Motors has 5 factories and Ford has 3 factories. Now then that's going to transition. There's going to be a transition to maybe a different set of factories for GM or Ford. And so then the probability of the transition will depend on the probability of where you are tomorrow. So omega prime is where you are tomorrow, conditional on where you are today and the actions that are taken by the players. So this is just the law of motion is a stochastic law of motion. The probability of being in a particular state tomorrow, omega prime, conditional on where everybody is today and what they do, is denoted by this. This is just simple probability stuff. The notation is uglier than the idea. And now the player receives a payoff at each time t as a function of where the state that they're in and the actions they take. Now, when you think about variety of things, like let's say you want to open up a new factory, and you see, in order to make this work cleanly, mathematically, existence proofs, etc., this transition has to be probabilistic. Now, but then you have to think, well, how do I model things like spending money on opening up a new factory? So the way that we think of it is that you may take some action, some part of your vector of actions could be something regarding making a new factory. So you may say, oh, I want a new factory. I want one more factory. But the thing is that you decide you want a new factory. Maybe you're going to get one, maybe not. And so if you're successful in getting the factory, then you pay the factory for the factory when it arrives the next day. So that's what this complicated notation is meant. It's like, you don't want to say, oh, I spent $1 billion trying to get a factory tomorrow, and then it doesn't come. We want to make it look like, make a decision and an attempt, and then I get a factory or not, and then I pay for it when it arrives. Nash equilibrium. Now, again, this looks like dynamic programming. Each player I, has a value function. By the way, this is infinite horizon stationary problem. So each player I has a value function, which is a function of the current state of the contemporary state. And that player maximizes his choice of actions. So his payoff, it depends on his action, which is adjustable. The vector of action of the actions taken by the other players. Now, this is not adjustable to player I. And now we're going to assume that every player has some strategy. And so that capital X of omega is a list of strategies. But my payoff depends only on, my actions only affect this piece of my payoff. And then plus beta times the expectation of where we are tomorrow. Now, maybe I did have a change that made me then cough up some money to pay for the extra factory. But then also there's the value of being at omega prime in the future. And then the conditional on also what the omega, all the probabilities are all conditional on what the state is today, what I did today, and what all my competitors did today. And so each player strategy is the argmax of that optimization problem. So this is a set of Bellman equations and policy solutions. Now, by the way, this is not dynamic programming. This does not have the contraction property. So in fact, we know for many reasons that these games can have many equilibria. So that means that we can't just proceed as we did with dynamic programming and believe that we're going to converge to a unique solution. No, instead, here's what is done in the Pockets-McGuire literature and even its refinements. First of all, you order the states. Now, what order you put them in, doesn't matter for any of this. Actually, since omega is going to be a multidimensional tensor, and so the whole business about ordering them gets to be kind of clumsy. You also typically want to assume symmetry, that that every firm basically has the same demand function, cost function, et cetera. So that everything is symmetric in that my value depends only on my state and then the distribution of people in the other states. Now, if you want to then impose that symmetry, then ordering the states so that the symmetric items are not double counted takes some skill. Now, Gautam-Gauss-Rankin many years ago had a scheme for doing that. So this is ugly kind of computer science kind of stuff. I don't know. Today I just probably write some script where the computer does something clumsy that would not require me to think. But you order the states. So you have state 1, omega 1, omega 2, omega 3. Now, you make some initial guess for the policies of each player in each state. Now what we're going to do is update the value function and the policy. So we're at some particular omega, and we're at some particular player, I. And so now what we do to get a new guess for player I strategy, you solve out player I's problem, given the current guess for everybody else's strategy. That's player I's new strategy, X super I, is the argmax of this over the X little xi. And then you plug that value into the payoff, and that's your new value for the value function at state omega for firm I. Now notice that it's not that I'm at a state omega and compute the Nash equilibrium amongst all the competitors. No, I'm just updating firm I's decision and value, holding fixed everybody else's. So this is like solving a Gauss-Jacobi kind of approach to solving the nonlinear equations. So now what we have to do is we order the states omega, but then also when we get to a particular omega in our list, we then update firm 1, firm 2, firm 3. So it's a simple updating kind of scheme. Now, I get rid of the big phi just to keep things simple. So then here's the hard part about this is that this expectation of the value tomorrow, conditional on where you are today and what everybody did today, is an integral. But even in simple cases, this can explode in terms of its computational complexity. Now, so suppose that every player, by the way, we're assuming that I'm in control of my state. It's like General Motors controls, General Motors and Mother Nature with the random variables, controls number of General Motors factories. But now suppose that each player, each competitor here, if he's at a current state today, maybe he can stay at that state, or maybe it'll go up, or maybe it'll go down. You know, maybe the number of factories goes up because you invest in a new factory, or maybe the number goes down because of depreciation. So each firm has 3 possible values tomorrow, even under the simplest model. Here, what we're doing here is we're restricting the model so that a firm only moves at most 1 step up or down. So there's 3 possible values for a firm tomorrow, and there's n firms, and so there's 3 to the n terms in this expectation, which means you've got a Recursive dimensionality. As you increase the number of firms, you have more and more terms exploding. Now, so that is a big computational problem. And so that's what happens is you end up spending a lot of time computing. When you have multiple firms, you spend a lot of time computing this integral. Now, the idea I had a long time ago, and that Ariel always said, it can't matter that much, doesn't matter, it doesn't matter. Anyway, then Uli showed up and I said, Uli, we're gonna do this. Uli was, Dorzelski was a postdoc of mine in the early 2000s. What we're going to do is replace discrete time with continuous time. We're going to stay with discrete states, but replace time, discrete time with continuous time. Now, this is a very, well, I think a big improvement on many dimensions. First of all, as we'll see, this eliminates the curse of dimensionality when it comes to computing those expectations. The other point is that I think continuous time is a much more sensible specification for real world problems than discrete time. Because by the way, when in the Fox and McGuire literature and all the applications of it, discrete time is often 1 year. Now, I'm not going to get into arguments about whether discrete time or continuous time is better if your unit of time is 1 week. In that case, I'm fine with staying with discrete time. But when you're talking about the unit of time being a year, then I really question the relevance of the model of any kind, because lots of things can happen in a year. For example, speaking of General Motors, I suspect that its perspective on auto sales this year has changed dramatically over the last few months. Things happen, stuff happens, stuff hits the fan and happens, and not just on an annual frequency. So real world decision making is more of a continuous time kind of dynamic. Now, one criticism that Uli and I ran into was that, well, the data that people have in empirical I/O is annual data. So therefore, the model should also be annual model, annual time steps. Now, I was very surprised when I heard that criticism, because I remember back in around 1980 or 81, I remember reading papers where they talked about this issue in macroeconomics. They said, well, now the data in macroeconomics usually comes maybe on an annual, some at a quarterly, few things at monthly intervals, but they're discrete time models. And I think quarter is about the most, for the data, the most common unit of time. Now, how can you think about continuous time models if their data comes in on a quarterly, with quarterly periodicity? And papers by Hansen, Sargent, and Sims showed that you can, if it doesn't matter, there's no need for the model to have the same time structure as the data, and went on to show how one could have continuous time macro models and use it even and for empirical analysis, even if the data was coming in only at a quarterly frequency. And basically what you have to do is you have your continuous time model, and then you make predictions about, given the parameters of the continuous time model, you then solve the continuous time model, and then you compute what the data process should look like if the data comes in a quarterly fashion. Now that's a non-trivial kind of computation, but that's what you can do. You can, from a continuous time specification, then do things such as compute the moments of a quarterly stochastic process, and then use that moment data to then back out what the parameters are of the continuous time model. So this, and then John Givicki had a paper in Review of Economic Studies in the mid-'80s that also showed this in a micro context. So this really surprised me when we ran into a frequent criticism about how, well, this is useless for empirical work in I/O because the data comes in at an annual frequency. That criticism is just false. It's just false, known to be false for almost 30 years now. So I just wanted to dispose of that possible criticism. Okay, so now we have continuous time. So there's some mathing that what happens is in a continuous time process, if you're doing actions X and your state is X, then there's a hazard rate, an infinitesimal probability of there being a jump at that particular time. Now, if there is a jump, the state is going to move to some new state with this density. So you have two probabilistic things here. First of all is the hazard rate of there being a jump, and then also the density of where you go if there is a jump. And this notation basically says this is a density of where you are at time t if the most recent state was omega sub t minus. See, the thing is that the problem is here that we can't say, okay, we're at time t, not what was the previous state. The previous state doesn't exist. It's a real line. But the limit of the previous states does exist because we're assuming the Firm's path is piecewise constant, right, continuous function of time. And so then also without loss of generality, we're assuming that if there is going to be a jump, you are going to jump. You're not just going to jump and then say, oh, excuse me, we're not going to move anywhere. So if there is a jump, something changes. Now, when you do this in continuous time, you see that over a short period of time, delta, the probability that the state at t plus delta has changed, that probability is equal to, that's what the hazard rate means, that the probability that the state changes over delta is proportional to phi of delta. Now, as if delta is positive, that it's not exactly true, but the error is on the order of delta squared. And then also, so the probability that if you do have a jump, that you're going to jump to omega prime is also some density, but also with an order delta error, because see, over a finite period of time delta, maybe you have two jumps. But the thing is that as delta gets smaller and smaller, the probability of having two jumps disappears. And so asymptotically, as delta goes to zero, you'll just have one jump. Now, the other thing is that if the transitions are independent across the firms, then what we have are that the joint probability of jumping is the product of the individual firms' densities. And so the probability that there is a jump in some firm is just a sum of their individual hazard rates. But remember that in a short period of time, there's only going to be at most one jump. And then in fact, there's only at most one jump by one firm. You're not going to have simultaneous jumps in continuous discrete state, continuous time processes. Now then, we can write down the same kind of stuff for the value function. This stuff gets pretty ugly pretty fast. We do a Bellman equation for a short period of time, but then we take the delta to zero and we end up with, and this now appears in the paper I sent you, this is now the continuous time Bellman equation. Basically, continuous time Bellman equation, by rho, when we go to discrete time, continuous time, we have rho as the discount rate. So you can think of beta, the discount factor in discrete time, as being e to the minus rho. Is how this usually translates. So the time rate of change of the value function equals the max of this Bellman equation. And then you can interpret this as flow plus. See, the problem here is that in continuous time, you have to rethink things because profits are a flow. But now the money that you may pay if you do have a transition is like a stock, and then the expectation of the value tomorrow is also like a stock. So you got to keep that in mind. Now in continuous time, your consumption is like a flow of wealth, and then the wealth is like the stock variable. Now, so then you go through the same kind of iteration on and on like this. Now, what we always did is Gauss-Seidel iterations, which means you immediately update everybody's strategy. When you update a strategy, it's immediately recorded, and then the new strategy is for firm I is used when you go and update the strategy for firm J. So it's a Gauss-Seidel substitution. The original Pockets-McGuire was Gauss-Jacobi, but then shortly after that, his students decided, well, let's do Gauss-Seidel because it saves on storage. You just have to store one copy of the value function and decision rules. Now, of course, that's a good reason. But remember, when you go from Gauss-Jacobi to Gauss-Seidel, you can dramatically change the dynamics of the iteration procedure. We do not have a contraction mapping here. That makes this irrelevant. No, you can get to different equilibria, and one Gauss-Jacobi can be stable and Gauss-Seidel unstable, or vice versa. So this is not just a modest change to save on RAM space. Now, so the Bellman equations here are really, like with dynamic programming, just a set of nonlinear equations. But it doesn't have the contraction mapping. There may be multiple solutions. But basically, what Pockets and McGuire did is just use a Gauss-Jacobi scheme to update things. Now, I don't think the phrase Gauss-Jacobi appears in the paper. Now, here's the somewhat interesting part is that I was the editor at Rand Journal that handled the Pockets-McGuire submission. And I liked the paper immediately. However, a lot of the jargon was statistics jargon, and so my main contribution was to push Ariel to write it more in a language that was more similar to what people familiar with games would understand. I don't know how much success I'd had in that regard, but that was my effort to make this to sort of downplay the statistics jargon and make more of a numerical and jargon and make it more accessible to people who didn't know all the probability stuff. But all they did is basically Gauss-Jacobi. That's what they did at the time. Now, again, by the way, let me say this. This paper was written in the early 90s. And even though you had more RAM in the early 90s than John Rust had in the early 80s, it still was a case that RAM was a problem. So yes, this is just a set of nonlinear equations. However, you could not think about trying a Newton's method or any other nonlinear equation kind of thing on this because you just didn't have enough memory to do this. So again, this is an example of a low storage algorithm that allows you to solve big problems, even though you don't have big RAM. So at the time, it was the state of the art for doing this. Now, what we do here in this table, what I talk about is you're asking now, how much do we benefit from going to continuous time? And the fact is we benefit enormously. So here's time per iteration, per state, per firm. So if you're trying to update, if you're at a state and you're trying to update one firm, how much time does it take? Now, let's not look at the 2-firm case. Let's look at the 8-firm case. By the way, the 8-firm case means that you have a million different states. And each state has, each state has 8 anyway, the number of unknowns is 17 million unknowns. And now updating each state with the discrete time, updating each state took 2/10,000ths of a second. Now, what's this percentage? And this is discrete time model. This is continuous time model. And so the continuous time model, this is, and basically the percentage is the percentage of time spent on computing the expectation. So if you're doing 8 firms, almost all your time is spent on doing that expectation. Now, if you had 8 firms, everything's the same except you have continuous time. What happens is that the time to update a single state has gone down by a factor of 100, of over 100. And why? Well, that's because only 58% of your time is spent on that expectation. Now, we also got a further reduction in time by some basic computer science, some data form structure or data representation thing, which could not be done with discrete time. It could be done with continuous time. And that got a further reduction in speed. So basically, you get, well, if you did all the fancy computer science storage stuff and as well as continuous time, you get almost a 300-fold increase in the efficiency of doing an update of one firm at one state. Now, the problem is, though, that by going to continuous time, you may have to do more iterations than you did with discrete time. And so this is time per iteration. Per state, per firm. And there, this is okay. This is the same as table 2 is the same as table 1, except we have more firms, and they had fewer states per firm. And so we get the same. In that case, 14 firms. We could solve 14 firms model in continuous time, or do the update 100,000 times faster. Okay, but now you may need more iterations in continuous time than discrete time, or you can get by with fewer. You don't know ahead of time. So what matters is how many iterations do you need before you can declare convergence. Now, convergence here means we say distance to the truth when the distance to the truth is 10 to the minus 4. More about how I determine that. But anyway, in discrete time, we see that continuous time basically takes a ratio. So this is this is like discrete over continuous. So we see that the number of iterations for the discrete time model is generally about half or a third as many, maybe even a smaller fraction of the number of iterations for continuous time. I'm not going to go into a complicated story about why this is the case. I don't particularly care to go into that kind of speculation. We know it's a different number. So before we make general comments about discrete versus continuous time, we should take that into account. However, the overall time, when you put the two together, and this is again 14 firms, up to 14 firms, 9 quality levels per firm. Here the state is how the quality of your product. And here the wall clock time is 29,000 times. Now, by the way, this isn't probably done by extrapolation. Anyway, yeah, I think the numbers in italics represent some extrapolation, because we weren't going to wait around for the. See, we did all the continuous time stuff, and then we sort of extrapolated for this. And so what we find is that overall you get for a small number of firms, let's say like a 75 increase in efficiency, and then for larger things, more like the improvement is in the order of thousands. So that's the continuous time approach can result in substantial improvement in running times by orders of magnitude. Now, the stopping rules. Remember my first or second lecture, I talked about stopping rules and about how you needed to, you generally don't know the rate at which this is going to, something's going to converge. And so therefore you should estimate the rate of convergence. Well, this is a paper where we do describe this idea and apply it. Because one thing that is true in empirical I/O is that they have a tendency to do these iterations and they stop when, let's say, the first 3 digits of everything agrees. They stop when the number of digits between 2 iterations agree. Now, as we saw in some examples, that's a very bad idea. Because you don't know the rate of convergence. And so it could be the case that even if things aren't changing in the first 3 digits, that doesn't mean you're close to the solution. Now, so then what we did is, but we were able to spend a lot of time to compute the truth. And the ad hoc rule was something like stopping, the details are in the paper. The ad hoc rule would be often stopping when it agrees to 3 digits or 4 digits, something. And what you see is that, particularly now when you had many firms, your distance to the truth, particularly when the discount factor was closer to 1, the distance from the truth could be large, much larger than you thought. So instead, what we did is we implemented this adaptive stopping rule that that I discussed in the first in the first week, where basically you do your iterations, you make an estimate as to the apparent rate of convergence, and then you think of that rate of convergence as the truth, and then you use that in judging whether or not you're close to the truth. And what we found is that what we found is that the convergence rate asymptotically was like almost basically, the convergence rate of 9953 means that the rate of convergence is 0.5% each iteration. So it's very slow. And so to get 4-digit accuracy, you have to go almost 2,800 iterations instead of the 589 that you might have thought you needed. And so this is shows how important it is. By the way, if you're trying to solve these models and do empirical work, remember with empirical work, you're trying to you need to not only solve these models, but you need to ask, well, how does the model change as you change a parameter? Well, so if you're doing empirical work, and this is how sloppy you're computing like in a nested fixed point thing, if you're doing this in your nested fixed point, and you're this sloppy, then I don't trust any number that comes out. Because if the lower level problem is being done in a very sloppy manner, then why trust anything that comes out? So basically, the computational gains here by going to continuous time are enormous. The crystal dimensionality associated with computing the expectation is gone. Now, can we do better? And the answer is yes, we surely can do better. And using massive parallelism is a way to do better. Massive parallelism with dynamic programming is a no-brainer because you have the key underlying operator is monotonic. Here, it's more dangerous, but I suspect that you do Gauss-Jacobi or Gauss-Seidel with dampening, and you will be able to take advantage of massive parallelization. Okay, this is a good time for a break. Any questions, any comments? Okay. Now, oh, I didn't want to lose that.
Sorry, Professor.
Yeah,
can I ask
sure.
a question?
Yes, please do.
I was wondering, I mean, for bringing the model in continuous time, anyway, numerically, we have to discretize also the time dimension, right?
No, 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 no. There's no discretization of time here.
Okay, but
There's
because
no discretization of time.
But that's, I mean, if we cannot compute the transition probability, I mean, if we have to compute them numerically, then we would have
Well,
to
no. Remember, the transition probabilities are given to you. I mean, that's something that you bring to the problem. No, there is no discretization of time here.
Okay, I see.
Yeah. No, this is something, thanks for bringing it up, because this is something I need to emphasize when I talk about it. There's no discretization of time here. None at all. You see, what economists are not familiar with is the topic of Markov chains in continuous time. And there's, now, if you're just doing simple Markov chains in continuous time, what you find is that things like the conditional densities or whatever can be written as matrix exponentials. No, there's absolutely no discretization of time here. That's one of the, I like that feature here.
Right.
But you see, in motivating the formulas, I talked about this capital delta discretization. But notice that I ran that to 0.
Right. It's in the limit. I was thinking about bringing the model, for what you said about bringing the model to the data, in which we to take a stand of what is the infinitesimal time dimension and carry it. I mean, move it forward to predict the process at the annual or whatever. So there we would need the discretization.
See, you see, the data may arrive in a discrete manner. However, the underlying, the process that generates the data could be a continuous time process. But so if you, I should write down some references to continuous time Markov processes. But basically in continuous time, you have what's called an infinitesimal generator, I think is the term. And so that's what I'm relying on here. And so what you can do is go from the infinitesimal transition probabilities, and by you see, this is a controlled Markov. There's a controlled Markov chain, so the math is a lot trickier. But if it was uncontrolled, then it literally is just like, you can solve this out in closed form. The transitions, given where you are today, what's the probability you're going to be in state I tomorrow, or a discrete time in the future? It literally is e to the matrix A times t, something like that. So there I'm trying to give an analog to this, and there isn't one. This is, by the way, one criticism we got here was that, well, there's some theorems that say that it's impossible to avoid the Kirsch dimensionality in these problems. And what that guy was thinking of was problems where you have continuous time and continuous state. That's not what we're doing here. We're holding fixed the number of states. And so it's just discrete time versus continuous time.
Okay, thank you.
Yeah. Now, so no, thanks for that because I do need to, in thinking in the future, I do need to make these connections with discrete state continuous time Markov chains. Thank you. Thank you.
Thank you.
Okay. Now we're going to take we're going to digress a bit into talking about nonlinear complementarity problems and applications. Now, I'm going to talk about very simple applications of nonlinear complementarity problems, then give you an example of using that to solve simple static game, but then point you to, I think, then point you to some work I'm doing with Carl Schmetters and Michael Ferris on dynamic games. Now, what, anyway, I could have chopped this down. Anyway, you're on your computer, you can, one way or the other, you can see this. You have the notes. Now, everything in economics is typically an equation. For example, we put inata conditions on utility functions so that the demand for a good is always positive. We don't like corner solutions. And also, we always make sure that in an IO model that a firm has zero marginal cost at zero output, so that they will always provide something as long as the price is not zero. Now, in international trade, there's the Armington formulation of demand, which basically assumes that all countries buy every good made by each other country. Now, this is a bit strange in many ways, but it's what the advantage of it is that it means that the demand for every good by every country is just the solution to a first order condition, an equation. Now, Barn constraints, well, we don't like Barn constraints because that also messes up Euler equations. But the fact is that life isn't represented by these equations so well. There are some goods for which my demand is zero, and it's not going to change no matter how low the price goes. And sometimes marginal costs are positive even at zero, and firms produce zero. And there are some things made in Italy that we do not want. There are some things made in the USA that nobody wants in Italy. This business of having this universe of goods that everybody wants a little piece of every possible good. This is just a fantasy. It has its analytical conveniences, but it certainly doesn't represent real world trade. So now, in order to understand problems where the solution might actually be zero supply or zero demand, we have to use what's called tools that comes from the part of computational math called nonlinear complementarity problems. And now here's suppose you have a function f and some x. And now normally you're saying, oh, I want to find an x such that f of x equals 0. Well, this is a generalization of that idea. This says that you're trying to find an x. So, by the way, suppose that you say, I want to solve for f of x equals 0, but I want x to be positive. Well, that may not be compatible, by the way. I want to solve where demand equals supply, but I want I don't want things like negative output or negative demand. So this comes up many times when you'd like to do an equation, but then you have some sort of non-negativity condition. So this is a nonlinear complementarity problem for f. This says you're trying to find an x such that f of x is greater than or equal to 0, and that x is greater than or equal to 0, So notice that both of these are x is greater than or equal to 0 and f of x is greater than or equal to 0. But you represent it as greater than or equal to 0, but you represent less than equal 0 less than equal to x here, f of x greater than or equal to 0 here. And in between, you put this perpendicular notation. And so what that says is that you also want that the inner product of x and f equals 0. Actually, what you really are saying you want for each I, either xi is 0 or f sub I, the I function is 0 at x. That's what you want. So complementarity requires that either xi is 0 or that the function f is 0 for each I, for each equation, for each pair. Notice that we're pairing up the, this can't be done arbitrarily. It's like we're pairing up each variable with one of the equations. Now this actually comes up naturally. So it generalizes a concept of equations. Now it's equivalent to a non-smooth system of equations where you say, I want the minimum of x and fi of x to be 0, which basically says I want one of them to be 0. Now, if all of the x's are non-negative, or if they're all strictly positive, then the result is the same as an equation. So this is a generalization of equations. Now, where have we seen this before? In constrained optimization. You're trying to minimize f subject to equality constraints and inequality constraints. And what do the KKT conditions look like? Well, the KKT condition says that you write down Lagrangian, and then you have these multipliers, lambda and mu, such that you have a first order condition holding, the equality conditions hold, and then the complementarity conditions, the multipliers mu for the inequality constraints, those conditions can be written in the complementarity fashion. That basically mu is greater than or equal to 0. The way I wrote it up here is that h has to be less than or equal to 0. So in order to stay with notation, I say 0 is less than or equal to minus h. And that we want that to be true for our solution for the mu and the x. And by the way, one of them has to be 0. So you've seen this idea before in KKT conditions. Now, what about the Arrow-Debreu model? Well, you've seen it there also in terms of the theory, because what happens is that every individual maximizes their utility. Oh, this is the social planners problem. Well, anyway, everybody. Okay. Oh no, so this is sorry. Yeah, this is for a person I wants to maximize his utility, subject to the constraint that the amount of money he spends is less than or equal to the amount of the value of his endowment. So this is an inequality constraint. And so then what we do is when we put together basically the first order conditions for the individuals has also a complementarity condition. And then for each market K, the price has to satisfy this condition that either the price of good K is 0 or the excess supply is 0. So again, you have in the problem, you have complementarity conditions. Those are examples of complementarity problems. And so basically the thing is that, remember, in all the examples we did with Arrow-Debreu, I said, solve for equilibrium and just take the first order conditions and set them equal to 0. Well, that's not going to give you a solution in some cases, but so this is what the general formulation is as a nonlinear complementarity problem. Now, with Nash equilibria, firm 1 wants to maximize X, subject to maximizing his profit, given what the other guy does, and also subject to some cost constraint. And so what you have there is that each player's optimization problem then is a nonlinear complementarity problem. You want X to be non-negative, and then you also want the gradient here to be non-negative, and then one of them should be equal to 0. And here the multiplier on the inequality constraint should be 0, or the constraint is active. And so now Nash equilibrium is really just written as this system of nonlinear complementarity conditions. So this notation, so basically the thing is for you to first get familiar with this notation and what this means. And also notice that now this is a generalization of what you've done before. Because in the past, when all you did is you say, okay, I want to find the optimal consumption, you just set the first, you just wrote down the first order condition and set that equal to 0. You rigged up the problem so that there were no corner solutions. But by the way, there often are corner solutions. Now, the solving these problems is, by the way, very, very common in applied general equilibrium. Now, by the way, applied general equilibrium is different than computational general equilibrium. Applied general equilibrium is basically where it refers to actual applications of algorithms for solving equilibrium problems. That's what applied general equilibrium is. And this is what they have to deal with. Now, how do you, and here's an oligopoly problem also. Let's say the market utility function is a summation of output, some CES kind of aggregator. And then each firm maximizes its profits subject to non-negative output. And so then the Nash equilibrium system is just denoted by this set of complementarity conditions. So now, how do you solve these things? Now, Todd Munson, in his PhD thesis at the University of Wisconsin, came up with the idea of sequential linearization and created the algorithm called PATH. I have no idea what PATH stand for. We just all call it PATH. So the idea was that you take your F. Yeah, so suppose your current guess is XK. Then what you do is you replace the nonlinear f of x function with a linear approximation around XK, your most recent guess. And now you have a linear problem where Z is unknown and where Z is the unknown variable. And now what you're trying to do is solve this linear complementarity problem. Now, so you solve this linear complementarity problem, and then that tells you a ray direction to go. And so then you search in that direction until you get to choose a new guess. Now, and then the merit function is kind of like a penalty function of sorts, but yeah, it's a generalized notion of penalty now. So basically, this is just a generalization of Newton's method for nonlinear equations. With Newton's method for nonlinear equations, this F is linearized around the guess, and then you solve for the solution to this linear equation to get your next guess. So this is just a generalization of Newton's method for nonlinear complementarities. And then in his thesis, he had to prove convergence of this and also wrote the code to make this work. Now, I'm not going to go into the details of this. This is not, this is too much math. This is as much as I know about the scheme. But I'm going to next talk to you about something called a semi-smooth reformulation. Now, what we do is we first define something called the Fisher-Burmeister function. Fisher-Burmeister function is a function such that it equals 0 if and only if A and B are both non-negative and A times B equals 0. This function is 0 if and only if either A is 0 and B is positive, or B is 0 and A is positive. Okay, that's a property of this function. So yeah, when is this going to be equal to 0? And what you now, if A equals 0, then B can be anything, because if A is 0, then you get B minus square root of B squared. So that's going to be fine, no matter what B is. Similarly for B. So, but now if you have if A is a negative number, then you have minus A plus B minus square root of A squared. We'll always take the positive square root here. So that if A is negative, there is no such B, such that this is equal to 0. So now what we do is we have a nonlinear complementarity involving xi and fi. What we do is we take each pair of variable and equation, plug it into a Fisher-Burmeister function, and then we end up with a system such that the ith equation in this system is the Fisher-Burmeister function. And now then we're going to treat this as a nonlinear system of equations. Now you might ask, how do you do this? Well, this appears to have difficulties because it's not perfectly smooth. But we'll see in the next example how we can smooth this out. So the available software, Path, is available. It's not in the public domain, but you can use it with GAMS or AMPLE. It is the dominant way, the dominant algorithm used for solving general equilibrium. There's a competing package, but I don't think anybody uses it. Then there's semi-smooth methods. Now I'm going to take you through some details of a semi-smooth approach to this. Why? Because it is possible to parallelize it through something called the TAO, the toolkit for advanced optimization. So that's why I'm going to show you the an example of semi-smooth, an application of semi-smooth. So now, here's a Mathematica notebook. So what I'm going to do is solve for a general equilibrium problem. I've written this up so that it can have up to 20 goods. There's a list of 20 goods. For this example, I just said, let's stick with 12 firms. So the number of firms equals the number of goods. And the goods, we're going to have a fish firm, a horse, steak, pork, ribs, etc. I include horse here because horse is legal in Switzerland. So now, so those are the 12 firms of differentiated products. So now let's construct the whole problem. The variables here will be the output, which also is going to be the consumption, but we're just looking at the firm's maximization problems, and that's the X sub J. Now the prices, this should also be P sub J, sorry. The price of the jth good is P sub J. Now what we're going to do is, the way we do this is that there's a market utility function, which is a utility function that represents aggregate demand. Now what we're going to do is choose a quadratic choice for the market demand function, which by the way is, a lot of times in IO examples, you write down things where all the demand curves are linear demand curves. And so that is the case with a quadratic, that's assuming a quadratic specification for utility. Now, so what I'm doing here, by the way, is creating, here's the utility function. You have a positive weight on each good, and then you have a minus x squared. So diminishing marginal return. So you have a quadratic, concave quadratic term in the utility function, but also then you penalize, the utility function penalizes you for having xi and xj to be very different. So this is trying to model what we see in that you want a little bit of everything. You want some of everything. You don't want to have wildly different amounts of consumption of two different goods. So what this means is then that you have cross partial elasticities that are non-trivial. So this is a pretty close to arbitrary scheme for IO models with linear demands. And so let's have a quadratic cost function. Now notice I'm going to have this term where the cost is quadratic in output, but then plus I'm adding this linear term. Now, if the marginal cost component is 0, then of course it's just a quadratic cost function, and of course, marginal cost at 0 output is 0. So that's why I'm going to do two examples. One where the marginal cost parameter is 0, and then another one where it varies across firms. Now, and then in these kinds of cases, if a firm produces xi, if the vector of x's is given, then the price that firm I gets is the derivative of the utility function with respect to that good. Okay, so then here's definition of profit. Now we're going to write down the first order conditions. So first order conditions are these derivatives. Firm I's profit with respect to its output. So we can construct a system of equations. And now, so we're going to just, if we had an interior solution, we could just solve for the system of equations. But I'm going to write down the first order conditions. Then I'm going to make random choices. This is to prove to you that this isn't rigged. I made random choices. Now I'm going to do semi-smooth. So I used that. Here's an example of this is a graph of the Fisher-Burmeister function. So if this is a Fisher-Burmeister function, this is actually simpler than the original Fisher-Burmeister function. And then I do a contour plot, you see exactly that it is 0 only on the non-negative axes. Now, so what I'm going to do is now apply, by the way, you have to orient these things. So my Fisher-Burmeister, I'm going to want the xi's to be non-negative. And then I want the first order conditions to be non-positive. Because what you know here is that if a firm may be stuck at 0 output because its marginal profits of increasing output is negative. So this is a natural condition. That if it's going to be 0 output, then the first order condition has to be negative, which means that if in a nonlinear complementarity problem, that means that the negative of the first order condition has to be positive. So now that's my nonlinear complementarity vector. I take the first order conditions and the corresponding output, and I construct this vector. I apply the Fisher-Burmeister function, and I apply this and construct this vector. And then here's now, one could just say, well, now I have a system of non-smooth equations, try to solve it, but no. What semi-smooth does is it takes the quadratic norm of this, and now this is going to be differentiable even at when A is 0 or B is 0. And so now we're just going to minimize this. And even though, so I had 12 outputs, and it solves quickly. Now, in this case, I chose 0 marginal cost. So this is a case where basically we could just treat it as a system of linear equations and we solve it. So we see here's the output of each firm, and of course they're scattered because I had random weights in the utility function, and everything works out nicely. And so now, oops. Okay, this slide is not supposed to appear there. Now we're going to put in fact, let me just deal with it. Well, who knows? Anyway. So now we're going to put in a case of where the marginal cost, basically the marginal cost of firm I is equal to 2i. So firm 1 has a marginal cost at 0 of 2, and firm 12 has a very high marginal cost. I do the same thing. I construct this, and then I do find the minimum of this nonlinear, the Fisher-Burmeister sum of squared errors. And now you display what happens. You see that the output for some firms is 0. And by the way, in particular, those firms that have the high numbered firms, the firms that have high costs, they're 0 output. But also, like even down here, firms 3, 4, and 4, even though their marginal costs were lower than firms 5 and 6 and 8, they have 0 output, and that's because the parameters were chosen randomly, and so it turns out that the demand for their good wasn't good enough. And so now the first order conditions, see, notice how they line up, and actually I think the next table, yeah, this is now what we see down here is a table. Here's the name of the good fish. Its output is 0.03. I mean, the magnitudes of these things don't mean anything. So it has positive output, and its first order condition is 0. It has positive profits, and then the price is 2.7, blah, blah, blah. Now, there's a small amount of horse meat demand for horse meat, and so its first order condition is 0. Now, it turns out there's no steak or pork. The demand for the steak and pork is not good enough to support the cost. You see, the marginal cost here was 6 and here was 8. And so basically there's 0 output, but the first order condition is appropriately negative, because what that says is that an increase in output by either of these firms away from 0 reduces profits. And then ribs and rabbits are in positive demand, and their first order condition is 0. So we see that when you line this up in these 2 rows, in each row, one of these is 0 and the other is positive. And that corresponds now to what you expect in a nonlinear complementarity problem. And now I just did some different algorithms here. It turns out that Newton is very slow, which is not surprising. Newton took 0.8 seconds. The conjugate gradient and quasi-Newton methods are much faster because they are not computing the full Hessian. And then for the heck of it, I just sent it off to a global optimizer, which means it was trying to solve searching for global, because now the problem is that this might have, when you start looking at the sum of squares, it may have multiple, it may have some extraneous local min, and this gets rid of that. Now, one thing I will point out though is that notice that I've set the target accuracy to be low, to be 6. Normally Mathematica would want to go for 8. This is a feature of these problems, is that because it's only there's the technical term here, semi-smooth, means it's smooth would be something that's C2 everywhere. Semi-smooth is something that's C2 in many places, but not globally. And so for a lot of the algorithms, being semi-smooth is enough for Newton style methods to work. So that's more jargon, but my objective here was to show you how to set up the problem. You write down you have a Fisher-Burmeister function. You create a list of Fisher-Burmeister conditions. Then you sum the square. You take a list of the Fisher-Burmeister equations, and then you just take the sum of their squares and then minimize, and that solves a nonlinear complementarity problem. So I just want to show you what such a problem looks like, and then also emphasize how. Okay, now if I gave you a problem where in equilibrium some firms produce 0, how would you proceed? Well, I don't know, but my guess is that many of you would say, well, first I assume that if every firm, I solve the equations assuming that every firm has positive output, and then I find out, oh, some firms have negative output. Then what would I do? Well, I'd set that firm to have 0 output, and then I'd solve for the others, hoping. And I just go bouncing around trying to, until finally I make a guess as to which ones have 0 output. And it turns out that the others are positive output. And even at those prices, the guys I thought would have 0 output still have 0 output. So it would be some complicated, headachy kind of combinatoric thing. It'd be a mess. All of that is swept away by this reformulation as a nonlinear complementarity problem. Just formulated as a minimization of a semi-smooth function, and you don't have to keep track of any of that. What's going on is that the computer is kind of keeping track of which should be 0 and which shouldn't be 0. That's going on inside. That's what the Fisher-Burmeister function is doing for you, and in a sufficiently smooth fashion that this can run quickly. Now, I think that's okay. Stop share. Okay. Now, that's the. I've just introduced you to the basic idea of what a nonlinear complementarity problem is, and I showed you one simple way to solve such, and then also pointed out that you have to be careful in terms of how much precision you expect in the answer. And by the way, 6-digit precision, 6-digit accuracy is good enough for most anything in economics, I would think. Certainly far exceeds what is considered acceptable. So that aspect of it is not something to be worried about. So now, what Carl and I and Michael Ferris, who was Todd Munson's advisor, have done is that we did this many years ago, but we got distracted by other things. We can write down these kinds of dynamic oligopoly equations, formulate them inside, well, we used GAMS, I guess, because that's what Michael likes, and then used path to solve that. And so now, and that works pretty nicely. Now, and the interesting case we had was one where firms have a choice of investment. Do you invest in terms of increasing your productivity or not? The other thing is you have a choice of having 0 output or positive output. So the idea is that some firms, when they're starting out, they may have a high cost, and so then they don't want to produce anything, but they work on investment, which reduces their cost. And so then you will see that initially they do no production, but then they do investment, and then they start doing production. And then perhaps what could happen is that the other firms have bad luck, and so their costs go very high, and you may just decide to stop investment because your cost advantage is so good, right? So what can happen inside that kind of model is a lot of complex things, basically modeling zero corner decisions, and that just comes out very naturally from solving these problems. How big can they go? I don't know. Now, my suspicion, by the way, is that that the original Pox and McGuire, I mean, if somebody wanted to do this as a project, I'd love it. That take the original Pox and McGuire model and then use some nonlinear equation solver that you have and solve it. And using the Python nonlinear equation solver with Casati and solve that problem. It's just a nonlinear system of equations. That's all it is. And a Gauss-Jacobi, Gauss-Seidel update scheme was what was necessary. That's the only thing that was possible, given the algorithm and hardware limitations that we had almost 30 years ago. I suspect today, even though people are still doing Pox and McGuire stuff, they're still doing it. My suspect is that can be considered as silly as doing using abacus to do calculations. That nonlinear equation solvers today can probably solve whatever Pox and McGuire did 30 years ago. Now the issue is size. How big can it go? I don't know, but even if you still had to go to a Gauss-Seidel, Gauss-Jacobi method with today's nonlinear equation solver, you certainly should do a block Gauss-Seidel method, block Gauss-Jacobi, where you take a block of the states, you solve for the Nash equilibrium, and then proceed in blockwise. So that whole literature, I suspect, is way behind the frontier on solving these models. Okay, so that's all I've got to say about dynamic games. Some of you may be aware that I've worked on papers where we solve for all the Nash equilibria in super games. That's more advanced material that I'm not going to mention during the course. So, but this is an example of games, discrete state games that are quite, that are commonly used, and I think are computationally much easier than most economists think. Okay, so I will now officially end the lecture.